Hi, welcome back. I have a little bit of a fun example here. It does have some relevance to what we're doing and some points I want to make, but I also thought I would show you some of the computational things you can do with these programming languages. This is a special relativity example. I'm going to show how I guess the main point is you can make your functions more readable, or your main more readable, by using functions. I'm going to be using a set of related formulas, 5 formulas. You imagine that you're doing some sort of a planning, an aerospace engineering planning job, preparing for an interstellar mission, and you're going to use these equations as part of your mission planning. And you would want to have those equations available to use as you need them, and then once you've got those equations programmed in functions, you could just call on them whenever you need them. That's kind of the idea. We could put these functions into their own header file, so whenever you need them, you just use the header file. You could have your own personal header file that's got your special equations in it, and just call on those whenever you need it, and you never even really have to look at the equation code again. You just use the functions as you need them. So that's kind of the point here. We would later take those functions, put them in their own file, and then you might not even have to look at them. You could call that a library of functions that you call on when you need them. The functions are related to each other, so they'd all go into the same header file. That's one way to do it, or you could put it into an object. Later we'll learn to use objects, and we could put these 5 functions in as member functions of a mission planning object if we wanted to do that. This particular functions we're using come from special relativity. The particular example is it's planning a mission to another star as an astronaut traveling in an ideal rocket. As far as special relativity is concerned, you might be really nervous about trying to learn about that. It's actually a fairly easy to understand subject once you've had your first 2 calculus courses and your first physics course. There's really nothing you can't understand about special relativity. This is the first thing that Einstein came up with in around 1904. He published this stuff. He even wrote a book later called A Simple Explanation That Everyone Can Understand. Apparently to Einstein, everyone knows calculus, but once you do have the basics of calculus down and elementary physics, Galilean motion, then you can understand this idea of special relativity. It's really not that hard. It's also, another reason I bring this up is even though this is a modern physics topic, it is actually something that some engineers use every day in their design work. It's something that we see all the time in satellite motion. It affects the clocks on satellites. It affects the behavior of satellites. And there's other engineers that deal with it in other areas, but that's the one I'm most familiar with because it changes the clocks on satellites. These equations are an improvement on Galileo's equations for constant acceleration motion. Those are the equations I'll show you. Now I'm also going to talk about an ideal rocket. This dream rocket would be able to accelerate at 1g indefinitely. 1g was the perfect acceleration for humans because that's the acceleration we grew up under. Our weight is like an acceleration. Einstein would actually say that the weight you're feeling is a force that is an acceleration. In his way of looking at things, the force of the ground on your feet is an acceleration keeping you from falling, and falling is the natural state. However you look at it, if you're in a rocket out in space and that rocket is accelerating at 1g, you can stand on the back of the rocket with your feet towards the back of the rocket, and it will feel like you're on Earth. It's actually undetectable without any very clever techniques. It's undetectable from standing on the surface of the Earth. Therefore, your bones would not atrophy, or your muscles wouldn't atrophy. Your bones would be strong because you're standing in regular gravity, or it would feel like that. Now, to make a rocket do that is way beyond our capabilities. Our rockets can accelerate at g for a while, but then they run out of fuel. So we'd need to figure out a way around that. But like I said, it's the ideal rocket. And then the idea is you fly halfway to another star, you turn around halfway there, and you start slowing down. And you slow down, you get to this other star just at the right time. Now the basis behind these equations is that after you accelerate long enough at 1g, you'll get closer and closer to the speed of light. A couple things about the speed of light. First, you can't go faster than that. Nothing goes faster than the speed of light. And as you get closer and closer, it's like you become heavier and heavier. To the outside observer, your acceleration seems to be slowing, and you're just creeping up closer and closer to the speed of light, but you'll never get there. To you, you're going to feel like you're always accelerating faster and faster, but you're still never getting faster than the speed of light. Instead, it seems like all the distances are shrinking to you. That's another effect we're not really talking about. The one effect, though, that is important here is that if the speed of light has to be the same to all observers, if you're in a spaceship traveling at 3/4 the speed of light, and there's a light beam flying along right alongside you, well, as that light beam passes you, it's going to appear to pass you at the speed of light, even though to the outside observers, they might suggest that the difference between your two speeds is 1/4 of the speed of light. To you, it's going to look like the speed of light. And the only way that works is if your perception of time is different than the one who's not moving. In fact, the stationary observer will always think that the moving observer is experiencing time more slowly than they are. And it works both directions, and there's no paradox or anything. It's all been worked out. It's all very well understood science, and it's proven every day in satellite motion to extremely high precision. We know that there's this time dilation effect. And in theory, you could take advantage of this when traveling to another star. Now let me write a couple equations down that are relevant here. If you had an acceleration that was constant, I'll call it A. A is a constant. And you integrate that, then, and you start from rest, then from basic physics you know that the speed, v, is the acceleration times time. That's what Galileo would say. Einstein said, well, that's fine as long as you don't get close to the speed of light. But once you get faster and faster, there's actually another effect that we're ignoring at low speed. Once acceleration times time gets large, then you have to fix that formula. Instead of A, I'm going to write alpha. That's alpha times t divided by square root of 1 plus alpha squared t squared. This is what Einstein said. Alpha is the same as A. It's also a constant acceleration. However, I've changed the unit system to do what physicists normally do in this situation. They change what v means, the units of v, so that v equals 1 is the speed of light. And this formula that I just wrote has a limit of 1. As time gets really, really big, the largest this number can get is 1. In the other end of the spectrum, in the other limiting case, when alpha t is very small, then the square root in the bottom is basically just 1, and the two formulas I've shown you are the same. But once alpha t gets sufficiently large, long enough time passes, then the speed varies from this first formula, and instead you have to use this more correct formula for velocity. Now, for my particular example, I possibly could use this formula. The rearranged version of this formula is t equals v divided by the alpha, the acceleration, times the square root of 1 minus v squared. All I did was rearrange for time. This same formula, this new formula, would be the one you'd use if you wanted to know how long does it take to get up to a certain speed, a certain fraction of the speed of light. V can't be bigger than 1, but if you wanted to know how long does it take to get to 0.9 of the speed of light, you could use this formula. You'd have to know what your alpha is, your acceleration in the proper units, but then you could see how long it takes to get up to that speed. Then I could integrate that first formula I showed you, and if I integrate it without considering relativity, Galileo would say it's 1/2 at squared. That's if I start from rest with a position of 0, then my acceleration, if it's a constant, times 1/2 times time squared is my change in position. Integrating the second formula I showed you, the correct one for using Einstein's equations, x is 1 over alpha times a difference, square root of 1 plus alpha squared t squared, and then outside the square root is a minus 1. These formulas look a lot different, but actually in the limiting case when alpha t is pretty small, if you did a Taylor series expansion of this square root term, then the minus 1 and plus 1 would cancel. One of the alphas would cancel, and you'd see that the two equations are the same in the limit case where alpha t is small. But as alpha t gets really, really large, then this equation diverges from the parabola behavior of the first equation. And it becomes more like a straight line behavior because eventually your velocity starts to be constant. It starts to be the speed of light. If I rearrange that formula for time, then I get a formula that I definitely will use in this example I'm about to show you. This is the time it takes to go a certain distance. It's 1 over alpha. Actually, this is the square root of alpha x plus 1 squared. And also inside the square root of minus 1. And that quantity then is just the rearranged version. It tells me how long does it take to go a certain distance x. So in my example, I'm going to put in half the distance to the other star. We'll figure out the time it takes to go halfway to the other star. Now, that formula is all great, but that's Earth time. To account for the fact that the astronauts have to be able to measure the speed of light as the same way an observer that's not traveling would measure it, we have a different time, tau, and this is just kind of a magic formula I'm going to show you, but it makes it so both the astronaut and a person that's not traveling with the astronaut, someone stationary, it makes it so they'll measure the speed of light as both as the speed of light. That's 1 over alpha times the natural log of alpha t plus square root of 1 plus alpha squared t squared. This tau is called proper time, or in this case it's the astronaut time. So that's the time it'll take, as far as the astronaut is concerned, to get halfway to the other star. If I plug in here the t that the Earth people are saying that it takes to get halfway to the other star. So it's a conversion from one time to the other. And I'll use those 5 formulas that I just showed you. I'll put them into functions. And then the other thing I wanted to mention is that ideal rocket business. If you're in a rocket, here's your rocket ship. Here's the nozzle, and there's jet fuel coming out the back or some kind of super fusion that's making this all work. You would stand like this, and the rocket would accelerate this way at 1g, and as far as you're concerned, you're on Earth. You could play baseball and do all jumping jacks and everything normal because the rocket is making it feel like you're on Earth. And that's the ideal rocket. The problem is, of course, normal rocket's going to run out of fuel, but if we invent some kind of super fusion rocket, then maybe you'll do that someday, and we'll be able to go travel to another star. All right, so let's consider the one quick diagram here. This diagram is on the website is called a space-time diagram. The funny thing about it is the time is on the vertical axis, whereas position is the horizontal axis. The y-axis is time, and it's also the line of our sun. We start here at the origin. That's our sun, and it's going to move right up the y-axis as time proceeds. Over here is the star we're planning to visit, and it's going to move straight up also, parallel to the sun. This red curve is the path of the spaceship in space-time. It starts off moving with the sun in this graph because it hasn't had time to accelerate very much yet. And as it accelerates away from the Earth, it's curving away, but it stops curving and eventually hits a straight line, and that's because it's running at the speed of light, and or very, very close to the speed of light. And then we get about halfway, I reverse the rocket, burn the other direction, start slowing down, and then we come to the star after however many years it takes. Then we hang out and collect rocks and put our flag down and do whatever we want to do. That's my delay time, where we just hang out and do our experiments. And then we come home, accelerate back towards the sun. Halfway through, we turn around, burn, and slow down, and we get back to Earth. And that's the mission plan to go visit another star. And then I've got the code in here to do this calculation. This is the prototypes for the functions. I developed the 5 very simple, most of them are simple functions. There's not very much in them. Each prototype is used for one of the 5 formulas I showed you. I've got time required. I've got something called velocity constant A. That's the velocity that you reach after a certain amount of time at a constant acceleration. The distance traveled, again, after a certain amount of time and a constant acceleration. That's a known number in this problem. I'm going to assume the acceleration is 1g, 9.8 meters per second squared, but then I convert it to the proper unit so it works with the formulas. But it's the amount of distance you travel after a certain amount of time. I don't actually use that formula in the run I'm going to show you. Instead, I use this time required formula, this first one, that tells you how long it takes to go a certain distance. I also could use this calculation time to v, which means the time to reach a certain velocity, and find proper time. I need that to convert Earth time to astronaut time. As far as the main function goes, there's a bunch of double precision variables related to this. For instance, total Earth time and total astronaut time. Those measure the time for the whole mission. The way I did it, I simply calculated the time it takes to go halfway to the other star, and then I multiply by 4. Once to slow down, and then 2 more times to come home. Altogether, there's 4 legs to the journey, plus that time in the middle, that delay time. That's the basic way I run this program. Then I have a more complicated way that the program could be run, which is to assume that you start accelerating faster and faster and faster, and you get up to, say, 0.99 the speed of light, and then you say, okay, that's fast enough. I can't watch out for space debris if I go any faster, so I'm going to stop at 0.99 the speed of light, and I'm going to coast now. I'm going to stop burning. I'm just going to coast at that 0.99 the speed of light until I get the right distance towards that other star, and then I'm going to turn around and start slowing down. And that's a more complicated version. I worked out the formulas for that too using these 5 functions. I won't actually run it that way, but one of the points of this example is that it wasn't really that hard to write that more complex version. If you look at the code and you try to understand what I did, you're just going to be looking at function names. You're not going to be looking at a bunch of equations, these complicated square root and natural log equations. Instead, you're just going to be looking at names. And you're going to look at the variables that go into the function, and you're going to look at what comes out of the function. And by looking at those functions, you get a very quick understanding of what this part of the code is doing, and you could actually write it or modify it much more easily than if all you saw was a bunch of special relativity formulas and you have to get out your special relativity book and remind yourself of how everything works. So anyway, these are the double precision variables mostly that I used. I did convert the acceleration to meters. I think I did it as meters per second per year, fractions of the speed of light per year, something like that. I had to convert it. And then I tell the user what we're about to do. I say, okay, how far away is the star that you're going to visit? How long are you going to stay there and collect moon rocks or space rocks? And how long are you going to coast? Is there a maximum velocity at which you're going to stop and start coasting? Or if you put in 1.0 here, then there is no maximum because you'll never get up to 1.0. So it'll just keep getting faster and faster and faster until you get halfway there, and then you turn around and slow down. That's the way I'll actually run it. Here in my first equation, it's actually a function call. I call that Earth time 1, and I calculate it by sending distance over 2 and acceleration to that function. Distance over 2, that's the distance that's halfway to the other star, along with the acceleration, which is 1g. I calculate Earth time 1, and at the bottom I'm going to multiply that by 4 since there's 4 legs to that journey. Then I say here, I check to see if we exceeded the maximum or not. I put in 1 as my limit. If I put in 1 as my limit, that'll never be true. But if I put in 0.99 as my limit, then it will be true. And what I'm doing, I'm checking here to see if after Earth time 1, have I gotten up to a velocity that's faster than my limit? And if I have, I go into that more complicated code. If I have not reached the limit, then I just go halfway, turn around, and start slowing down. This part of the code is some function calls to calculate the issue of where do I start coasting and how long do I coast before I turn around and slow down. If I don't have any coast, then my coast time I set to 0 for both the astronaut time and the Earth coast time. That's what I'll do here. So there is no coast time in the middle. Instead, I just find out what the maximum velocity was that we reached using my velocity constant A function. That tells me how fast I'm going after a certain amount of time. I send to that function acceleration and Earth time 1. I'm not using pass by reference on any of these functions. I'm just using pass by value. each function returns a single number back to the main. It's a standard way of programming. Pass by reference is really cool, but if you don't need it, there's no reason to use it. And I didn't feel like I needed it on this code, so I just used pass by value. One advantage of pass by reference would have been so I could have had a logical or Boolean value as an output in addition to the numeric value. That would maybe improve these functions, but I decided not to use that. All right, after I've calculated the coast time or set it to 0, then I calculate total Earth time. That's 4 times my Earth time 1, twice my coast time, because there'd be 2 coasts in there, though I'm going to run it as if it was 0. And the delay time adds on to that too. That's the time we just hung around and at the planet, explored. Then I calculate the astronaut time. For that, I need astronaut time 1. I use my find proper time function, and what I do is I send Earth time 1 and the acceleration, and it returns how much time passed as far as the astronauts are concerned. And that's astronaut time 1, and then I do the same calculation. 4 times that number, plus twice the coast time, if there was any, plus the delay. And after I wrote this program, I got out my general relativity book. It had a section on special relativity at the start. Double check to make sure my answers were right, because we had examples like those kind of examples in there. It's like I say, it's really common stuff. Every physics major studies this stuff. Only certain kinds of engineers actually study this stuff if they need it. It's more of a graduate topic, but it's a fun topic. If you've ever read science fiction, a lot of authors like to use this. They think this is a really neat thing to try to use in their science fiction. Someday, well, it's partly reality already. Someday it may be full-blown reality, this kind of stuff. But let's run the program and see what numbers we get. It says this program calculates the time required for an astronaut to travel to a star and back using a spacecraft that can accelerate indefinitely at 1 g of acceleration. So the distance to the star from Earth in light years is what it asks for. There's 2 stars that are close. Alpha Centauri in the northern hemisphere, Alpha Proximi in the southern hemisphere is a little bit closer. They're both about 4 light years away. So I'll put 4 light years. Our first star we're going to go visit besides the sun. And it says enter the amount of time in years that the astronaut will spend at the star. I'll put 1, so we're going to hang out and collect rocks for a year and do experiments. And the maximum speed, I'll put 1.0. There's no maximum speed in this case. And hit enter, and it gives me all the answers. It says the astronauts will travel to the star, spend 1 year at the star, and then return. The spacecraft reaches a speed of 0.946 the speed of light. Now, that's a pretty cool number. What that means is that if you fell for 2 years, approximately, you still would only be 95% speed of light. That's how fast the speed of light is. Kind of interesting number to look at. Part of that's because you're slowing down as you get closer, but mostly it's just that the speed of light is so darn fast. The very best you could ever imagine doing this trip is 9 years. 4 years to somehow get there, instantaneously be at the speed of light, travel there 4 years, 1 year at the star, 4 years back. The minimum amount of Earth time that could pass to go to a star and back and spend a year at the star would be 9 years, 4 plus 1 plus 4. We got back in 12.17 years, which is pretty good. 3 extra years because of the acceleration and deceleration. The astronauts are 7.8 years older than when they left. So they've aged 7.8 years. Let's run it again. This time I'm going to put 20 light years. One of the neatest experiments, I think, that astronomers have talked about is the idea of an optical baseline telescope, very long baseline telescope, where unlike currently it's all done with radio, or mostly done with radio. You've seen the pictures of the big radio dishes, the astronomy. It's like a giant radio dish. You got a bunch of radio dishes all lined up, and they can move them. They can combine their signals. Even if they're all across the world, they can combine their signals and make it like it's one giant radio signal. Well, the dream would be that we could do that in the optical spectrum. One place we could do that is on the dark side of the moon, and astronomers have talked about that because the geology is much better on the moon. There's no atmospheric interference on the moon. They've talked about doing it there. Actually now, that was when I was in grad school, like 14, 15 years ago. Now they're talking about actually being able to do that on the surface of the Earth because they've learned new tricks for how to account for atmospheric effects. So that'd be really amazing if we could do that. Because with that sort of telescope, we would have such fine precision. We could look at stars, and we could look at we could actually look at the planets around other stars, Earth-like planets. Right now we can't do that, but in theory we could look at Earth-like planets around other stars and analyze their atmospheric content through the absorption and emission lines in the spectrum that we see in the light coming off that planet. And we could quickly identify which ones nearby are likely to have are likely to have life. So let's say 20 light years away, that's reasonable. Maybe there's some planet we found out there that's got life, we think. So we send our astronauts off. They're going to spend a year collecting plants, and no maximum speed, let's say. The spacecraft gets up to a speed of 0.996 the speed of light. That's constantly accelerating for the first half and constantly decelerating for the second half. When we get halfway, we're going at 0.996 the speed of light. It takes 44 years for them to get home, which is pretty good considering it was 20 light years away. 41 would be the very best you could ever do. The astronauts have aged 12.9 years in their journey. So their kids are now older than they are, possibly. Run it again. This time, let's say we've made contact with life, intelligent life, 200 light years away, and we want to go visit them. We'll go talk to them for a year, and no maximum speed, just for simplicity. So 200 light years away, the spacecraft gets up to 0.999956 times the speed of light. So assuming you could fly that fast without running into space debris, then you would get home 404 years after you left. You'd only be 21 years older than when you left because of the relativistic effects. It's pretty cool. It's not quite as amazing as science fiction authors might have you think, and no one's invented such a rocket yet, but it is interesting to think about, and it's all real science. It's just currently unattainable as an engineering project. So anyway, that's it for that example. If you're wondering what the point of all that was, mainly it was the idea that there's these collected functions, these related functions, and we could put them all in a library or a header file and call them then as we needed them. If we were a physicist or an aerospace engineer writing these kind of programs, we'd want to do that because we'd be writing a lot of these kinds of programs, and we'd want to always have those functions available. And that's it for this example. Thank you.